On October 24, 1944, the Sibuyan Sea became the focal point of the most concentrated aerial assault in naval history. The target was the Imperial Japanese Navy battleship Musashi. This was not merely a ship, it was a floating fortress displacing 72,800 tons at full load. She was the sister to the Yamato and represented the absolute zenith of battleship engineering. The United States Navy threw wave after wave of aircraft at her with a singular engineering objective. They had to overcome her reserve buoyancy before she could retreat. The battle that unfolded was a contest between static defense and dynamic energy. The American pilots hammered the ship with an estimated 19 torpedoes and 17 bombs. These numbers come from United States assessments. The Japanese records indicate lower figures of 11 torpedoes and 10 bombs. The discrepancy is academic because the physics result was the same. No ship ever built could withstand that level of saturation. The hull was designed to resist gunfire from 18-inch battleships, but it was not designed to repel a swarm of torpedoes striking the same side repeatedly. To understand why she sank, one must understand the concept of reserve buoyancy. A warship floats because the volume of water it displaces weighs more than the ship itself. The empty space inside the hull acts as a bubble of lift. Every time a torpedo breached the hull, that bubble got smaller. The Musashi engineers fought a desperate battle of counterflooding. When the port side took on water, the ship began to list or lean to the left. To correct this, the engineers deliberately flooded undamaged compartments on the starboard side. This added weight pulled the ship back to level, but it consumed the critical reserve buoyancy. They were trading altitude for stability. With every counter-flood, the ship sat lower in the water. By the evening of October 24th, the limit was reached. The bow dropped 13 feet. The sea washed over the forecastle. The laws of physics, which had been stretched for 9 hours of combat, finally snapped. The ship began a slow roll to port. The men on the bridge were not fighting an enemy fleet anymore. They were fighting the ocean, and the ocean does not negotiate. The massive hull lost its righting arm. This is the geometric point where the center of buoyancy can no longer push the ship back upright. As the Musashi rolled past 90 degrees, a terrifying mechanical failure occurred. This is a detail that sets this wreck apart. The ship was armed with 3 main turrets, each housing 3 18.1-inch guns. These turrets were held in place by gravity and massive roller paths. They were not bolted to the deck in a way that could support their own weight upside down. As the ship capsized, the thousands of tons of steel comprising the turrets slid out of their barbettes. They plummeted to the seafloor separately from the hull. This was the moment the ship ceased to be a weapon and became a falling object. The Musashi disappeared beneath the surface, taking 1,023 men with her. The sinking was not the end of the violence. As the hull descended into the dark, it faced a new enemy. Hydrostatic pressure began to squeeze the compartments that still held air. Somewhere in that descent, a catastrophic event occurred that would hide the ship from the world for decades. The location of the wreck was known in general terms, but the specific coordinates on the bottom of the Sibuyan Sea remained a mystery. For over 70 years, the final resting place of the Musashi was a blank spot on the map. It was a war grave protected by depth and the limits of sonar technology. The story of the battle ended in 1944. But the story of the salvage survey was just beginning. It would require a new generation of technology to find what remained of the greatest battleship ever lost. 1,000 meters of water creates a barrier more effective than any steel armor. To reach the resting place of the Musashi, one must descend into a world of absolute darkness and crushing pressure. The battleship lies at a depth of approximately 3,300 feet. This is not the abyssal plain of the deep Atlantic, but it is a hostile environment that forbids casual access. For 71 years, this column of water protected the wreck from looters and scrap dealers. The ocean floor in the Sibuyan Sea is a volcanic landscape covered in deep silt. It is a place where history is preserved by isolation. The depth is only the first wall. The second wall is legal. The Musashi is a designated war grave. Under international maritime law, she remains the sovereign territory of Japan despite lying in Philippine waters. This legal concept is known as sovereign immunity. It means that the wreck cannot be touched, disturbed, or salvaged without the explicit permission of the Japanese government. This is a non-recovery site. There are no plans to raise the hull or cut into the steel to recover gold or artifacts. The mission that launched in 2015 was strictly a visual survey. The goal was to document the site without violating the sanctity of the tomb. When the survey team finally illuminated the site, the first thing they had to contend with was the scale of the destruction. The ship did not land as a single coherent unit. The violence of the sinking, combined with the underwater physics, created a scattered debris field. However, certain components survived with remarkable clarity. One of the most striking images from the survey is that of the port propeller. The screw itself is a massive bronze casting. In the deep water environment, it has remained surprisingly clean, free from the heavy marine growth that consumes wrecks in shallower water. It still shines in the lights of the underwater vehicle. But the story is in the steel shaft connected to it. The drive shaft appears to be bent. This is a detail that speaks to the kinetic energy of the impact. It suggests that the stern section hit the seabed with catastrophic force, perhaps while the shaft was still rotating, or simply from the sheer weight of the hull crushing down on the drivetrain. This bent metal captures the violence of the end in a way that dry statistics cannot. The environment down here is silent, but the arrangement of the wreckage screams of chaos. The reserve buoyancy that failed on the surface was replaced by the dead weight of flooded steel. As the ship fell, she likely reached a terminal velocity that tore weakened sections apart. The pressure at 3,300 feet is roughly 1,500 pounds per square inch. This is enough to implode any sealed compartment that had not already flooded. The survey revealed that the stern section where the propeller is located landed upside down. This inversion is common in battleship sinkings. The heavy guns and armored superstructure make the ship top-heavy. Once the stability is lost, the hull naturally wants to turn turtle. The Musashi followed this laws of physics to the letter. The stern lies inverted, burying the aft turrets and the rudder in the mud. The bent propeller shaft stands as a sentinel over this inverted mountain of steel. It is a mechanical testament to the forces that ripped the pride of the Imperial Navy apart. The darkness of the Sibuyan Sea has preserved these details, perfectly freezing the moment of impact for 7 decades. 8 years of historical analysis preceded the first physical ping on the sonar. The search for the Musashi was not a simple matter of sailing to the coordinates listed in the battle reports. In the chaos of 1944, navigators under fire were rarely precise. The research team had to triangulate data from 4 different countries to narrow down the search box in the Sibuyan Sea. It was a logic puzzle that required sifting through topographical data and old naval archives before a single piece of hardware touched the water. In March 2015, the years of paper research finally converted into kinetic action. The expedition was led by Paul Allen aboard the yacht Octopus. They were not looking for a needle in a haystack. They were looking for a steel mountain in a mountain range. To achieve this, they utilized a 2-stage technology approach that defines modern deep-sea survey work. The first stage involved an autonomous underwater vehicle, or AUV. This is a robotic drone that swims independently of the mothership. It is programmed to fly a grid pattern over the seabed, much like a lawnmower cutting grass. It uses side-scan sonar to paint a picture of the bottom using sound waves. The AUV is the scout. It covers vast areas of the ocean floor looking for anomalies. It does not see with cameras, it sees with acoustics. When the AUV detects a hard return that looks like man-made metal rather than volcanic rock, the team marks the coordinates. Once the anomaly was identified, the team deployed the second stage. This was the remotely operated vehicle, or ROV. Unlike the autonomous drone, the ROV is tethered to the surface ship by a cable that carries power and data. It is flown by a pilot on the surface in real time. The ROV brings high-definition cameras and lights to the target. It is the difference between seeing a shadow on a radar screen and seeing a photograph of the object. As the ROV descended to the target zone, the cameras revealed a debris field that confirmed their calculations. But in a survey like this, finding metal is not enough. You must prove the identity of the ship. This is where the small details become more important than the massive guns. Amongst the twisted piping and hull plates, the cameras focused on a specific industrial artifact. It was a valve wheel, likely from an engineering space deep inside the ship. This valve wheel was significant because of the markings. On the rim of the wheel, characters were visible. They were Japanese. In the middle of the Philippine Sea, finding a valve with Japanese writing is the forensic smoking gun. It linked the wreckage directly to the Imperial Navy. It is a strange paradox of salvage that a 70,000-ton battleship is often identified not by its massive armor belt, but by a small brass component that a sailor would have turned by hand. The discovery was confirmed. The team had located the Musashi. However, the data streaming back up the tether revealed a reality that was difficult to process. The ship was not sitting upright in one piece, as some had hoped. The sonar maps and the video feed showed a scene of absolute devastation. The sovereign immunity that protected the site legally could not protect the structure physically. The survey team had found the target, but now they had to decode the scatter pattern. The wreckage was not just a ship on the bottom, it was a crime scene of physics that suggested the Musashi had destroyed herself before she ever hit the floor. The bow lies upright and proud, yet the stern lies upside down and the middle is missing entirely. This is the logical paradox that defines the wreck of the Musashi. When the survey team mapped the site, they found the vessel in 3 distinct conditions. The bow section is remarkably intact. It sits on the seabed with the deck facing up as if it were still sailing. The anchor chains are still run, and the teak deck has rotted away to reveal the steel beams beneath. But as you move aft past the number 1 barbette, the ship simply ends. The stern section tells a different story. It is inverted. The massive weight of the rear turrets and the steering gear caused it to flip over during the descent. It slammed into the silt upside down, burying the screws and the rudder assembly. But the most disturbing aspect of the survey data is what lies between these 2 massive sections. The entire amidships section is gone. The citadel, which housed the boilers, the turbines, and the magazines, has been reduced to a field of shattered debris. This is where the science of debris field forensics comes into play. By analyzing the scatter pattern of the wreckage, experts can reconstruct the timeline of the breakup. If the ship had broken on the surface, we would expect to see 2 large, distinct halves lying relatively close to each other. That is not what the autonomous mapping revealed. Instead, the data shows that the ship left the surface intact. She began her dive as a single unit. The destruction happened in the water column. As the Musashi descended, the internal pressure began to build. The ship was on fire internally, and as the hull rotated, the machinery tore loose from its mountings. The forensics point to a catastrophic event known as a hydrostatic explosion. This occurs when the cold water of the ocean meets the superheated steam of the boilers, or when the air pressure inside a compartment fails to equalize with the water pressure outside. The result is a detonation that rivals a torpedo impact. In the case of the Musashi, it is highly probable that one of the magazines detonated or the boilers exploded violently as the ship capsized. The evidence for this violence is scattered across the seabed. One specific artifact captures the scale of this internal failure. Lying amongst the twisted plates is a boiler. This is a massive cylinder of high-pressure steel that should be deep inside the armored heart of the ship. Instead, it is lying exposed in the mud, partially burying other debris beneath it. For a boiler to be ejected from the hull, the ship had to be torn open from the inside out. It suggests that the hull girders snapped and the ship effectively unzipped, allowing the heavy machinery to spill out into the ocean. The survey confirms that the Musashi did not just sink, she disintegrated. The 9 hours of desperate damage control on the surface kept her afloat, but they could not save her from the physics of the deep. The engineers had managed to keep the ship level enough to fight, but once she rolled, the structural integrity failed. The loss of the amidships section explains why the wreck was so hard to identify for so long. There is no iconic silhouette of the bridge standing tall in the darkness. The bridge structure itself was ripped away and lies on its side in the debris field. The forensics tell us that the ship died twice. First, she was killed by American aircraft, and then she was obliterated by her own physics during the fall. 15 tons of steel anchor still hang from the bow, a testament to the scale of the engineering. Nothing on the Musashi was built to human scale. It was built to the scale of empires. The anchor alone weighs as much as a standard city bus. The main battery guns were 18.1 inches or 460 millimeters in caliber. Each turret weighed more than an entire destroyer. When you look at these numbers on a spreadsheet, it is easy to imagine a salvage operation that brings these massive artifacts back to the surface for a museum. However, the survey conducted in 2015 made one conclusion absolutely clear. There will be no recovery. This was the decisive outcome of the expedition. The decision to leave the Musashi on the bottom was not just legal or ethical. It was dictated by the physics of the wreckage. The ship is not merely broken. It has been structurally obliterated in a way that makes lifting impossible. The culprit was the internal pressure spike caused by the magazine detonation. While the hydrostatic pressure initiated the crush, the detonation of the ammunition magazines delivered the final killing blow. When the ship capsized, the propellant stored for the 18-inch guns became unstable. The resulting explosion did not just breach the hull, it shredded the heavy armor belt and vaporized the internal bulkheads that provided structural rigidity. The debris field forensics show that the midsection was blown outward with such force that the steel plates are twisted like wet cardboard. To lift a ship of this size, you need structural integrity. You need a hull that can withstand the tension of lifting cables or the buoyancy of attached pontoons. The Musashi no longer possesses this integrity. The amidships section is a collection of disconnected plates and machinery lying in the mud. There is nothing to attach a cable to that would not simply tear away. The survey team realized that any attempt to disturb the main wreckage would likely cause it to collapse further into the silt. This reality solidified the mission profile as a non-intrusive survey. The success of the operation was not measured in tons of steel recovered, but in terabytes of data captured. The team used the ROV to inspect the 18-inch gun turrets that lie upside down in the sediment. These turrets fell out of the ship when she rolled over. They are now separate, distinct objects on the sea floor. Even if the legal protections of the war grave were lifted, the engineering challenge of raising a 3,000-ton turret from 3,000 feet is practically insurmountable. The expedition proved that the true value of the Musashi is not in the metal, but in the history it represents. The survey achieved its primary objective by positively identifying the wreck and documenting its condition. The images of the 15-ton anchor and the scattered guns provided the evidence needed to close the file on the sinking. The decision not to lift was the only logical engineering choice. The ship remains a sovereign territory of Japan and a permanent tomb for the crew. The survey team left the site exactly as they found it, taking nothing but high-resolution imagery and leaving nothing but respect. The outcome was a successful digital recovery of the ship while leaving the physical steel to the deep. We know exactly where she lies, yet the discrepancy in the hit count remains unresolved. The survey data mapped every square inch of the debris field, but it could not answer the fundamental arithmetic of the battle. United States pilots claimed 19 torpedo hits. The Japanese combat logs recorded 11. The violence of the disintegration means the steel itself cannot testify. The hull is too shattered to count the impact holes. This numerical gap is a permanent feature of the history, leaving us with a paradox where the precise location is known, but the precise cause of death remains a matter of debate. The only number that is absolute is the human cost. When the Musashi slipped beneath the waves, she took 1,023 men with her. For over 7 decades, their final resting place was an abstraction, a general circle drawn on a chart of the Sibuyan Sea. The discovery in 2015 converted that abstraction into a specific set of coordinates. It transformed a missing in action file into a confirmed war grave. The visual evidence collected by the expedition offers a haunting commentary on the fall of the empire that built her. On the extreme bow of the wreck, there is a mounting point for the imperial seal. This was a massive 16-petal chrysanthemum, the symbol of the emperor. It was originally carved from teak and covered in gold leaf. In the environment of the deep ocean, the organic wood has long since rotted away, the gold likely detached or disintegrated. What remains is the negative space. The steel mounting bracket is still there, framing an emptiness where the symbol of power used to be. It is a perfect metaphor for the ship itself. The structure remains, but the spirit and the purpose have dissolved into the dark. The environment that holds the Musashi is defined by hydrostatic pressure. At a depth of 3,300 feet, the water exerts a crushing force that is constant and unyielding. This pressure is what likely caused the final catastrophic breakup during the descent, but now it acts as a form of preservation. The deep water is low in oxygen and the temperature is near freezing. This slows the rate of corrosion. The bronze propellers shine as if they were polished yesterday. The bent drive shafts and the scattered ammunition cases are locked in a state of suspended animation. The survey did not attempt to disturb this equilibrium. The legacy of the mission is not a recovered artifact sitting in a museum glass case. The legacy is the digital resurrection of the ship. By mapping the debris field and identifying the specific components like the valve wheel and the anchor, The team provided the only kind of closure possible for a ship of this magnitude. They proved that the Musashi is not lost. She is simply keeping station at a depth where humans cannot go. The decision to leave the wreck untouched respects the boundary between salvage and desecration. The magazine detonation that gutted the ship created a scene of devastation that no engineering project could reverse. The success of the survey lies in its restraint. We now possess a complete high-definition record of the disaster. We can study the load paths that failed. We can analyze the debris scattered to understand the physics of the sinking. But the ship remains the property of the sea and the men who died on her. The coordinates are no longer a mystery, but the silence at 3,300 feet is absolute. The Musashi has been found, but she will never be recovered.